get as close to back on schedule as we can. This is AE-445 spacecraft detail design, and I'll present Team Descent and Michaela Dahlstrom.
Good morning, everyone, and thank you so much for coming today. My name is Michaela Dahlstrom, and I am the project manager for Team Descent, and we are here today to talk to you about Project Hummingbird. I'll be going over today's briefing outline, the Team Descent overview, and our Project Hummingbird concept of operations and overview. Today's briefing will address the overview of Project Hummingbird, the breakdown of our subsystems within Team Descent, along with our requirements, design metrics, testing, integration, and summary from our project. First and foremost, I would like to introduce my assistant project manager, Simon Polger. Kyle Miller, structures lead. Alkana Riley, propulsion lead. Dakota Breckland, electrical lead. And Eric Vieira, systems lead. You'll be meeting the rest of the team further along in today's briefing. At the beginning of the preliminary design phase last semester, Team Descent was presented with a few stakeholder needs, which included having a reusable aerial payload delivery system that could soft land a payload in a precise and predetermined area. After looking at systems such as the lander, glider, and parachute systems, ultimately the Skycrane was chosen. To further elaborate on what a Skycrane is, I'd like to present to you our concept of operations. First and foremost, the payload is put into the Hummingbird system. The Hummingbird is then turned on, and a systems check is performed to ensure all components are operating correctly. The Hummingbird then ascends to an altitude no greater than 150 feet. It does not have to spend the entire sortie at its altitude, but we need to be able to reach it in case we need to traverse above or around obstacles. In addition, the Hummingbird system does not have to fly completely level. It can travel up towards a 45-degree tilt angle as long as it's stable and steady. Once it reaches the payload destination, that's when Skycrane operations begin. The payload will be lowered on a series of 3 tethers to the landing zone. The solenoid claws will retract. The tethers will be retracted back up into the Hummingbird system, which will then reorient and reascend to an altitude of no more than 150 feet and safely travel back to a second predetermined area where it will be soft landed in order to await another delivery. Behind me, you're going to see a condensed version of our requirements tree. Please note that the requirements in white represent system-level requirements, while the colored ones represent subsystem level. Specifically, the green boxes are for electrical requirements, yellow for structures, and blue for propulsion. We are not going to be looking at each one of these requirements in depth due to time constraints for today's briefing. However, if you have any questions about the requirements that are not being talked about, please feel free to ask us about it during the Q&A session at the conclusion of today's briefing. In order to introduce you to our requirements, all of these requirements are branched back into 4 major requirements. Requirement 1, relating to being controlled by one operator. Requirement 2, talking about the transport and delivery of the payload. Requirement 3 will refer to the survivability and reusability of our Hummingbird system. And finally, the 4th requirement for the aesthetic appeal of the Hummingbird system. At this point in time, I'd like to introduce my assistant project manager to talk about the configuration management and integration of the Hummingbird system.
Thank you, Michaela. My name is Simon Polcher. I'm the Assistant Project Manager for Team Descent, and I'll be talking to you about the configuration management of Project Hummingbird. The configuration management document is essentially the assembly instructions for Project Hummingbird. The project was broken down into 5 major subsystems. Behind you, you see a system arc, and our 5 major subsystems including top cowling, top hub sheet, boom assembly, bottom hub sheet, and the payload assembly as well. Here you see an actual diagram of how it all fits together. The top cowling that you can see in the diagram or on the physical system is printed out of ABS plastic. The ABS was surprisingly resilient, which was fortunate because this houses all of our delicate flight electronics, including our flight computer, our receiver, and our GPS unit. Our initial cowling survived several crashes and protected the system. It acted as kind of a spring buffer, which protected all of our critical systems and our batteries as well from any puncture, which is important with a LiPo battery. The top hub sheet is constructed from carbon fiber and serves as the base for our power system. So all of the batteries were attached to it, as well as the Skycrane system, which you can see here in the center. That's our winch motor for the Skycrane. And underneath is the spool for the Skycrane, which you can just barely make out inside the physical system. The bottom hub sheet served as the basis for the system and was the attachment point for the landing gear. The landing gear was another surprisingly resilient portion of our system. We did, unfortunately, experience several hard landing events, some of them upside down. But the landing gear managed to survive a 20-foot drop when one of our batteries unexpectedly failed. And the damage was somewhat significant to the landing gear. 3 of them were bent, 2 of them severely. But the system was undamaged, and more importantly, there was no fracture caused to the carbon fiber plates. And that was a definite bonus for us, as those are pretty expensive and difficult to manufacture. The booms serve as the structural component which attaches our propulsion system on. So that serves to get the props a safe distance away from our cowling, and also provides a moment arm for easier control and stability of the system. The payload is attached via the 3-tether system that Michaela mentioned earlier, and those tethers run through the bottom cowling and the bottom hub sheet and attach to the spool here, as well as being attached to these 3 payload claws you see here, and you can see on the physical system as well. The payload is then lowered via a 25-foot tether, which is spooled up inside on the spool, and released via the solenoid actuated claws. Along with the configuration management, we have a bill of materials that lists every component. So behind you, you see the bill of materials for the top cowling, and you can see the amount of detail this goes into. We have everything from low-res solder to all of our connectors, antennas, etc. This serves as continuity for any further projects or anyone who is interested in how we built the system, and also serves as continuity for the university to make sure that we're tracking all the materials we used. Now Kyle Miller will talk about the structure subsystem and how this system was used and how it met some of its requirements.
Thank you, Simon. As I said, my name is Kyle Miller, and I'm going to be introducing my structures subsystem, as well as some of the critical structures requirements. So first, we have Ethan Higgins, our liaison to the integration team. We have Simon Polsher, also the assistant team lead. We also have David Wright. And so the critical structures requirements are that the Hummingbird structure shall be capable of remotely detaching the payload during a sorting. The maximum payload impact velocity shall be 3 foot per second threshold and 1 foot per second objective. Finally, the Hummingbird vehicle components shall survive at least a 3 foot per second landing. So the first requirement I will be going over is shown here on your requirements tree. And it pertains to the remote detachment of the payload from the system. And what we looked at to design this was obviously the release of the payload using claws. To analyze the claws and to determine whether they would actually release from the payload, we looked at a physical clearance in CATIA, as well as some hand calculations on paper. For testing, all we looked at was whether the claws would actually detach during testing. So the requirement satisfaction value for this requirement was that there was a successful detachment of the payload. It was desirable for this to be a consistent and predictable occurrence. Our analysis told us that the claws would detach with a 1.1 margin in CATIA, as well as a 1.5 static margin using hand calculations. In testing, 10 out of 11 tests with the claws successfully detached, and during flight, we had 5 flights where 4 times the claws successfully detached when the user prompted it. So we determined that this requirement was both analytically and experimentally satisfied. The next requirement I will be going over is shown here on your requirements tree. And it pertains to the payload impact speed. The way we designed our spool, our single spool for lowering the payload, was we looked at the RPM of the motors and we determined what radius we needed to touch down the spool, to touch down the payload at a slow enough speed. So we did dynamic modeling using the simple equation you see here, as well as the RPMs of the motor. And we found, For testing, our method for testing was to look at video from our landings and look frame by frame using a reference measurement pole to find distance, and we would determine velocity in that way. The requirement satisfaction value was less than 3 foot per second impact speed, and our analysis told us that we could do this with between 0.49 or 0.71 feet per second, assuming a perfectly hovering Hummingbird. In the test, after looking at the video, we determined that we had a 1.19 feet per second impact speed, and the discrepancy between the analysis and the test comes pretty obviously from the imperfect hover of the system. So we determined that this requirement was both analytically and experimentally satisfied. Now I'd like to bring up David Wright to talk more about structure subsystem.
Thank you, Kyle. As he said, I am David Wright, and I will be continuing on with the critical requirements for the structure subsystem, as well as improvements that suggested by the structures team for testing and analysis. The next critical requirement to be discussed falls under the third branch pertaining to the survival and reusability of the system, in particular the vehicle survival of an impact of 3 feet per second or greater. For the performance metrics, the survival of physical components, the landing gear, the airframe, cowling of a typical landing were considered. For our analysis, we performed an ANSYS dynamic workbench simulation where we simulated, in particular, one of the landing gears with the entire system weight on one end impacting the ground at 3 feet per second. Whereas for actual testing, we took the physical system completely assembled with electronics and motors attached and dropped it from a height of about 2 inches to simulate a slightly greater than 3 foot per second drop. Now, for the requirement to be satisfied, we would need to survive a drop of at least 3 feet per second. For our analysis, we estimated impact force of about 95 pounds, which, given our weakest cross-section on the landing leg, would give us a 1.6 margin of safety. Whereas for the actual physical testing, we did drop the entire system, and afterwards we checked through the parts. Every part was intact and the system was functional afterwards, as we believe the requirement to be satisfied experimentally and analytically. Now, for improvements that could be made for the structure subsystem, for the remote payload detachment, initial considerations for the solenoid claws could have been made better with considering the circuitry involved in the wiring, as well as possibly selecting a lower power solenoid claw for possible smaller wires and better spool. For maximum payload impact speed, initial analysis did not consider enough uncertainty with the Hummingbird's vertical hover, so including more uncertainty factors in the analysis would have helped, as well as pushing for a more stable system as opposed to the mobility we were aiming for in the requirements. For impact survival, analysis could have been improved by modeling the entire system in ANSYS, which was not done for time and experience reasons, as well as discerning the actual properties of all materials to be used, as opposed to speculating on similar materials such as the rubber and the boots. Now I'd like to bring up Alcon Riley, propulsion lead.
Thank you, David. My name is Alcana Riley. I'm the propulsion subsystem team lead. Today I will be introducing the propulsion subsystem team and going over our critical design requirements. Sorry. The propulsion subsystem is made up of myself, Nasser Al-Matari, as our systems liaison, and Michaela Dahlstrom. The two critical requirements for the propulsion subsystem include not contaminating our payload with our landing surface substrate and producing 44 pounds of total thrust. I will be discussing the 44 pounds of total thrust requirement first. It is located on the requirements tree behind me. So, we first had to analyze what kind of system we would use to produce this thrust. Due to lack of time and our knowledge, we decided to use electrically powered aerodynamic propellers because they are safe and easy. We used a MATLAB code once we had chose our components to analyze whether or not they would survive the amount of amperage we would need to draw in order to make our 44 pounds of total thrust. Once we had procured our components, we put them on the college's test stand, as shown behind me. Please note the stand does not have the motor installed in this picture. So from our analysis of the motor's spec sheet, we found that we would produce right at 11 pounds of thrust per motor. This is a very tight tolerance to our requirement. However, that was the best we could do with our component choice and available funds. From our testing, our very first test resulted in a thrust of about 8.6 pounds for that one motor, so about 2.5 pounds less. This is due to atmospheric conditions on the day of test, which resulted in a low pressure area, thereby reducing our total amount of thrust. We therefore had to conduct another test under more suitable conditions. This resulted in a greater thrust at 11.8 pounds of thrust. Lastly, due to unfavorable flight characteristics later on with our system, we had to change our propeller choice. Therefore, another test was required, which resulted in an 8-pound total thrust. Therefore, this does not satisfy our subsystem requirement. Next, Nasser Al-Matari will discuss the next critical propulsion subsystem requirement.
Thank you all. My name is Nasser Al-Matari, and I will be discussing the second subsystem critical requirement and suggested improvement. The second subsystem critical requirement constrain how much landing surface substrate is allowed to contaminate the payload. The requirement's location is denoted by the tree behind me. The height at which the vehicle hovers dictates the amount of surface substrate which will be moved by the propeller's downwash. In order to find this height, we use a proportionality test. This test used different smaller but similar system to find the hovering height of each without disturbing the landing substrate. We then use a MATLAB code to extrapolate from the data using our system's weight. The value was solved to be 20 feet. We tested this at approximately this height. The requirement says that the only 5% of the top of the payload can be contaminated. From our analysis, at 20 feet altitude, no payload contamination should occur. After the test, a scan of the payload found that 2.4% was contaminated, which satisfied our requirement. That can be seen from the picture. The substrate was disturbed during the payload delivery operations. The improvement to proportional subsystem critical requirement include first reducing the thrust to weight ratio value or increasing the total system for the thrust requirement. Second, changing the concept of operations and conducting a more precise proportionality test to better anticipate the surface substrate contamination. Next, I'd like to bring up Dakota Portland to talk about electrical subsystem requirement.
Thank you, Nasser. I'm Dakota Berkman. I'll be discussing the electrical subsystem as well as the critical requirements for the electrical subsystem and the horizontal and vertical deviations. So in the electrical subsystem, I'm the lead of that. I have Ashley Bergstrom today, who's going to be presenting with me. Jennifer Deal is also in the electrical subsystem. And Kim Christel is the electrical liaison, but also in the integration team. And Jesse Rodriguez is the last electrical member. So the critical electrical requirements, there are 4 of them. There are the Hummingbird shall have within a 5-foot circular radius. There's a vertical constraint as well. And there's also energy storage time and life cycle of the energy storage devices. So the first one we're going into today is the horizontal hover. So the horizontal deviation design metric was the maximum error we allowed during hovering over the target area. Using analysis method for this was using manufacturer data for the Skycrane, for the flight computer. And then test method was using an onboard camera and yardsticks and marking flags to determine the area in which the Hummingbird was hovering. During the deviation maximum value we accepted was a 5-foot circular radius. The analysis outcome from the manufacturer data was a 8.2 circular radius. The test outcome was with pilot input was actually 4.69. Therefore, this requirement was experimentally satisfied, but not analytically satisfied. Next requirement we're going into is the vertical deviation. Vertical deviation is the error during hover, how high and how low the Hummingbird can deviate off of the desired point. For this, the analysis method was using manufacturer data, and the test method was using a 10-foot pole and a camera in line with the pole, with the Hummingbird right next to the pole to measure where the hover height was deviating to. The satisfaction value for this was less than 3 feet deviation. During the analysis, it came out to 2.6 feet during windy conditions. This is from manufacturer data. And test outcome with pilot input is 2.25 feet radius. Therefore, this requirement was analytically and experimentally satisfied. Next, I'll bring up Ashley Bergstrom. Can you talk about the electrical subsystem?
Thank you, Dakota. As he said, I'm Ashley Bergstrom, and today I'll be discussing the performance metrics, the testing and summary for the critical requirements regarding battery time and battery cycle, as well as discussing some of the improvements for the electrical subteam. The location of the first requirement regarding the battery time is located on the requirements tree behind me for your convenience. And the performance metric that we use for the first requirement regarding battery time was to determine the total operational flight time of the Hummingbird. We did this analysis method using MATLAB code, which gave us an estimated theoretical value of what that operational flight time would be. For our test method, we used a video timestamp off of the video footage shot on the day of testing, and that gave us our actual operational flight time. In order to satisfy this requirement, we needed to attain a threshold goal of 10 minutes and an objective goal of 12 minutes. During analysis, it was determined that we would reach both of these goals with a time of about 14 minutes, 13 minutes and 52 seconds. Unfortunately, during testing, we were only able to achieve about 9 minutes, but it's important to note that we believe one of our batteries was not fully charged during this testing, but there was no way for us to actually verify this. And due to delays and other time constraints, we were unable to retest, which means that this requirement was left unverified. So although we analytically satisfied it, we were unable to experimentally satisfy this requirement. The location of the next requirement regarding battery cycle is again highlighted on the requirements tree behind me. And the performance metric associated with this requirement was determining the number of full sorties completed without any energy storage component replacement or repair. We used previous experience from team members as well as outside research to determine that the LiPo batteries would be our limiting factor in this. For our test method, we determined we would need to complete 10 full sorties in order to prove that we could support the amount of cycles we needed for this requirement. In order to satisfy this requirement, we needed to attain a threshold goal of 10 cycles or an objective goal of 15 cycles. And during our analysis, for the LiPo batteries, the ones that we chose, they were shown to support over 500 cycles. But again, due to delays and time constraints, we unfortunately were only able to perform 2 full cycles of our batteries. But it's important to note here that a full cycle of our battery means that it was discharged to 80% and then fully recharged. So although we did use our batteries more than 2 times, we only did that full cycle process twice. So unfortunately that was just due to time constraints, which means that, again, this requirement was analytically satisfied, but not experimentally satisfying. Lastly, I'd like to go over some of the improvements that we identified throughout the semester. The first being that we would have chosen a flight computer that was more customizable for our purposes, and also one that provided feedback during the programming stages, which would have helped a lot during the first part of detail, as well as choosing a battery that had a higher milliamp hour rating, so we could have had longer flight times. Next, I'd like to bring up our systems lead, Eric Vieira, to speak on the systems requirements.
Thank you, Ashley. My name is Eric Vieira. I served as the systems lead for Project Hummingbird. And today I'm going to be introducing the integration team. I'm going to be talking about our critical system level requirements. And I'm going to be discussing our delivery radius requirement and our thrust to weight ratio requirement. The systems team is made up of myself, Sean Akana, and our liaisons, Nasser Al-Mutari, Ethan Higgins, and Kenton Christel. So our critical system level requirements that we're going to be looking at today are that the Hummingbird should be able to deliver a payload within a radius of 10 feet, that it should have a thrust to weight ratio of 2.0 with the payload attached, that it should complete at least 10 sorties, and that it should have an aesthetic appeal rating of at least 70% when shown to ERAU-Prescott, Arizona faculty and staff. So the first thing that we're going to look at today is the delivery radius requirement. It's shown here on the requirements tree. For this requirement, the performance metric that we analyzed was the payload delivery distance from the intended landing point. Our analysis method was specifications provided on the manufacturer data sheet for our flight computer, and our test method was comparison of the payload landing point with respect to where we intended to land it. The graphic here shows the intended landing point as an X, and concentric circles representing radii that enclose the areas for which our threshold and objective satisfactory values would be met. So the satisfactory requirement value for this performance metric was a 10-foot threshold and 3-foot objective delivery distance from the intended landing point. The outcome of our analysis was that we would be able to deliver the payload within 4 feet of the intended landing point, and during testing we were actually able to land it at 3 foot 9 inches. So we were able to verify this requirement both analytically and experimentally. Next, we're going to be looking at the thrust to weight ratio requirement, which you can see on the requirements tree behind me. For this, the performance metric was the thrust to weight ratio of the vehicle and payload combination. And the analysis method was calculating the expected total thrust based on our engine and propeller combination and comparing that to the expected system weight of the vehicle and the payload together. Our test method, was estimating the thrust generated by the system using the test stand and the load cell, as Elle described earlier, and comparing the total system thrust with the cumulative weight of the summed system components. The requirement satisfaction value was at least a 2.0 thrust to weight ratio. And in our analysis, we hit exactly 2.0, but during testing, our final configuration used a 1.74 thrust to weight ratio because the initial configuration proved to be unstable, which led to crashes in our initial tests, which really delayed our testing regime. So we added weight and we reduced the propeller size to make the vehicle more stable. Thus, our thrust to weight ratio was reduced. And because of this, this requirement was analytically but not experimentally satisfied. Here you can see a diagram that explains our thrust test setup. In the middle is the thrust test stand itself. And over here you can see a representation of our motor propeller assemblies. There's also mounting hardware in the load cell that was used to record the thrust generated, as well as associated electronic hardware which was used to excite the motor and propeller combination and record values from the load cell. Next, I'm going to bring up Kenton Christel to continue talking about the electrical subsystem. Systems, subsystem.
Thank you, Eric. My name is Kenton Christel, and I'm going to be going over our last two critical system requirements and also overall system improvements. So as you can see, this is the first requirement that I'm going to be going over, and this is our reusability system level requirement. And the performance metric that was associated with this requirement was the number of sorties that our Hummingbird could complete. And our analysis method for this was to analyze the max cycling capability of both the batteries and the structure. And the test method was to actually perform sorties with the Hummingbird. So our requirement satisfaction value for this requirement was at least 10 sorties to be completed. Our analysis outcome proved that the batteries would be capable of at least 500 cycles at an 80% depth of discharge and a structure capable of more than 1,000 cycles underneath nominal landing conditions. For our test outcome, we had completed one sortie, but this was due to time constraints and not due to system limitations. So this requirement was both analytically and experimentally, this requirement was analytically satisfied, but not experimentally satisfied. The last requirement I'm going to be going over is the aesthetic appeal requirement. And the performance metric for this requirement was the percentage approval of the aesthetic appeal of the Hummingbird according to the ERAU-Prescott campus staff and faculty. Our analysis method and test method were both surveys, but the analysis was using the Hummingbird CAD model as the visual, and the test method was to use the actual, or pictures of the actual system that we had created. So the requirement satisfaction value for this requirement was at least a 70% aesthetic appeal rating, and an analysis outcome showed that we had a sample mean aesthetic appeal rating of 83%, and the test outcome was that we had a sample mean aesthetic appeal rating of 90%. Therefore, this requirement was both analytically and experimentally satisfied. Finally, I'm going to be going over some overall systems improvements for our system level requirements. The structures team suggested that we would redesign the spool, including the slip ring connections, to allow for greater reliability of our Skycrane system. The electrical sub-team suggested that we would create a mock-up of the system before integrating it onto the vehicle itself, allowing for more time for integration and testing. And a lot of our conditional failures could have been mitigated by this. Also, we would have consulted with experts in the UAS field to help select our flight computer, as that also caused some issues. For the propulsion team, they suggested that we would relax the thrust to weight ratio requirement to something more realistic so that the system would be more controllable. And for systems, we suggested that we would place the component orders sooner to allow for additional time for integration and testing. Now I'm going to bring up Michaela Dahlstrom.
Thank you, Kenton. Once again, I'm Michaela Dahlstrom, and I will be concluding today's briefing with a requirement satisfaction table, budget, scheduling, a video montage, and some lessons learned and acknowledgements. Our very familiar requirements tree is once again behind me, however, the color coding has now changed. The green requirements are the ones that we were able to both analytically and experimentally satisfy. The gold ones are the ones that we did not even attempt to try to experimentally satisfy due to safety, time, and budgetary constraints, and the red ones are the ones that we were unable to experimentally satisfy. There are 35 requirements on this tree, 25 of them passed, 4 of them were not tested, and 8 of them technically failed. However, Team Descent is completely confident that with another week of optimal flying weather conditions, that 6 of those 8 failures could have been turned into successes with retests. Our budget for Team Descent was $2,900, and of that we only used $2,669.04. Though the electrical and propulsion teams both went over budget because of having to buy replacement parts due to those crashes, we had a management reserve of $660, and that allowed us to stay under budget overall within the team. Our team hours came out to be 5,272 between both prelim and detail semesters. Please note that the blue slice of pie is from engineering, and that was the actual integration, testing, and building of the Skycrane along with operations. The engineering management is going to be the light green, and that was basically preparing for anything like this, preparing for meetings, preparing for testing, trying to get everything organized. The dark green deals with the administration, the dark green deals with professional development, which is research and consulting with the experts in given fields, and the yellow is the administration. Here's a video montage for Team Descent. And I can assure you the payload and the Skycrane was not damaged in that last photo. That was just a bunch of exhausted engineering students having fun. Some lessons that we've learned is that you should always plan for extra time for integration testing, because no matter how well you think you've planned something out and how amazing your design is, something will always come up and you will always need to take a little bit of extra care to make sure your system works. So always plan for extra time. To always calibrate your equipment in the right conditions. As you can tell from the thrust test, the amount of thrust that we produce varied vastly, and that was because some of our tests were performed in nice, sunny, 70-degree weather, and our equipment was calibrated in those conditions, but the optimal conditions occurred at 3:30 in the morning at a nice, crisp 40 degrees Fahrenheit, so obviously our data was a little bit corrupted because of the calibration issues. You should try to confront all of your design problems early on. As much as you want to try to stay on schedule and work around it, it will always come back to haunt you, so try to engineer a solution that will maintain the fidelity of your system as early as possible, and to never be afraid to ask for help. Team Descent would like to thank everyone who has helped us out along this journey, specifically our professors who not only gave us an amazing education to fall back on for this project, but who were always willing to help us even though we were not registered for their prescribed classes. To our pilots, Thomas and Riley, who not only flew our system, helped us debug it, was there every step of the way, and did it for absolutely no financial reward or academic credit. For Ms. Izzy Albert, who not only made our animation in the beginning, but also our video montage in the end. Today's panelists for taking time out of your day to come offer our feedback and advice on our project. We really appreciate it. And to Dr. Yale and Professor Mangum, you two have played two of the biggest roles into shaping us into the engineers that we're about to become. And the qualities that you bestowed in us not only make us good engineers, but good people as well. We're really lucky to have you guys as mentors. And finally, to my team. Without each and every one of you giving 110% literal blood, sweat, and tears, with banding together in times of failure rather than ripping each other apart, this project was a success because of all of you. So thank you so much for this incredible journey. And that officially concludes today's briefing.
There's a microphone at one end or another. If you want to start at one end and at least introduce yourselves or ask a couple of questions, we'll let the audience know who the panelists are, and actually some of the team members know who all the panelists are then too.
Okay, I'll just do introductions, and then you can start down there, so I don't have to ask questions first. I'm Kayla Martin. I'm a faculty member in the Aerospace Engineering Department here on campus.
I'm George Carlisle. I'm from the Jet Propulsion Laboratory.
See, I'm Scott Blue. I'm retired from working on military classified payloads for the NRO. And so right now I spend most of my time in Prescott, Arizona.
Jacob Alder, got about 4 years experience working on military payloads. First, I'd just like to say, nice job. Working with quadcopters and payload delivery is not an easy challenge, and I'm very impressed with what I've seen with this, and I'm sure you've realized that there's a lot of challenges in working with this sort of system. I think going to my first question on slide 31, you may have touched on this and I may have not been paying attention, so I apologize. But my question pertains to, you noted that there was a difference between your analytical results and your experimental results, and I was curious to see what you think the reason was for that delta.
The main reason for the change is as atmospheric conditions, specifically as temperature changes, the thrust output changes. Excuse me for a sec, could I get slide, could I get slide 129, please? So this slide here shows you the differences in densities for as temperature changes, and so this, using density that basically adjusts for the amount of thrust that you're capable at. Excuse me. Our motor supplier basically did all their testing at very near sea level, and we're at 5,000 feet here, so there is quite a discrepancy in altitude.
Okay. Pertaining to your aesthetic appeal requirement, that I enjoyed. My only comment on that is I would have liked to have seen your analysis of alternatives, just what constituted appealing and what didn't. And then lastly, the one thing I noticed with your testing and your verification, I didn't necessarily see a lot of emphasis put on the test engineering itself. A lot of what could have helped mitigate some of the risks that you observed was understanding the conditions for your go, no-go conditions, your risk acceptance and mitigation. It could have helped you kind of avoid trying to test during adverse weather effects, and probably could have helped you save just a little bit of time. Just some things to consider in the future.
We did have requirements that we were not able to fly in weather where the wind was more than 10 miles per hour or any sort of precipitation whatsoever. Those were our two biggest requirements. And a lot of the failures wasn't due to weather, but due to some calibration issues with our ESC to our motors. The motors would not spool up at the same rate. So what happened is that, as you can tell, it would flip because one of the motors would go full blast while the other ones were idle, causing the system to flip over. So that's where a lot of our problems came. 2 of the 3 crashes resulted from that.
Okay, so expanding upon that just a little bit, were any tests conducted in the laboratory environment to kind of verify the spool-up times of all motors involved?
Yes, after the first crash, what we did, first thing we did was take off the propellers and we tried to recreate those conditions. We actually ran into some very interesting results as the motors would spool up both random, we cannot repeat it, and it was very sporadic, and it was never the same twice. We were able to have the help of Riley Griffin and Thomas car who were able to figure out why it wasn't working. It actually came from our flight computer. Also the fact that when we calibrated our accelerometer, which was on board, it was at an angle from the table, and we had to go recalibrate it within the Hummingbird system, and that was able to solve the problem. But there was quite a few number of reasons as to why it was happening that way.
Okay. Very well, thank you.
Just a couple of comments and questions. First of all, really good presentation. I sat through dozens, if not hundreds, of design reviews for space contractors that are designing systems that are worth hundreds of millions of dollars, and I can tell you the presentation is right on with what they do. In some cases, even better. It's amazing how much time they put into their process, and at times the process doesn't turn out a very good product. The product was very good. It was very entertaining, very legible. You guys did a great job with the presentation, so I want to congratulate you on that.
Thank you.
Just a couple of thoughts. I'm sure that time constraints did not allow you to do some of the requirements that for this kind of a project you would certainly have to think about, particularly safety, which I didn't see any mention of concern about the thing taking off on its own and flying into a building or flying into a car, or, you know, if you're actually using this to deliver a product, you want to have some kind of fail-safe mechanism so that if something does go wrong, it lands nice and softly and doesn't hurt people, that kind of thing. So, you know, that would be something that you would have to build into your design review and presentation and everything. If you had more time, I'm sure that was part of the problem.
We did have some safety measures. We had a kill switch that would automatically shut down the motors in case if something happened. We also, in order to avoid the unfortunate takeoff without permission, was that we had an arm and disarm switch, so that way it wouldn't even activate unless our pilot told it to start arming and get ready to fly.
Okay. Let's see, the hover testing that you performed, I'm sure that you had didn't really discuss the ambient requirements that you had for that, but I'm sure that they were all done under no wind conditions. And I was wondering if there was ever a thought to build in some kind of wind variation as a requirement that you have to be able to meet.
We definitely did not have a wind requirement when it came to the substrate, so that would definitely be something we would go back and try to incorporate into that requirement, because we didn't even think to do that.
Let's see, one other thing was this aesthetics requirement was, I have to echo his interest in, I've never seen or heard of anything like that before. I don't think very many people care exactly how the product looks as long as it does the job, so I'm curious as to why you had to have that.
I have to take the bullet on that. I've done enough of these projects where they sort of got it to work, but it looked cruddy. So I challenged them back in prelim, and I said I would like for it to look professional. I would like it to be something you'd be proud to display, something we might be able to get out in the future for a preview day or when we had people from off campus here. So they turned that into aesthetic appeal, and we've got a lot of feedback over this.
In all honesty though, we completely support this requirement, because one of our stakeholder needs was for this to be a legacy project in which the campus will pull it out on like open house days, like Dr. Yale said, to show prospective students what senior engineering students are capable of. And with that, as Dr. Yale said, they weren't going to pull out a project and save it if it kind of looked like it got slapped together. So we knew there had to be some level of craftsmanship that was inside our system. And to try to quantify and objectively get a requirement from a rather subjective need was very interesting. However, we do support this 100% because even the first company that comes to my mind is Apple. It may not be an outright requirement, but in all their advertisements on the internet, on television, they not only talk about the functions of their new product, but also using phrases such as sleek new design that kind of pertain to the aesthetic. So having the aspect of aesthetic in marketability, which we're essentially trying to market this as a legacy project to the campus, was really important. So in order for us to have mission success, we have to meet those stakeholder needs, which is ultimately where our requirements come from. So we knew we had to have that in there. So it wasn't just Dr. Yale telling us. We knew we support this 100%.
Next thing was, you guys learned firsthand that you actually gain a lot more knowledge from failures than you do from successes. And I just point out that most people don't know about this kind of stuff, but the original NRO intelligence program, the Corona program, the first 13 launches failed before they got success. So you guys didn't have 13 failures, so you're doing better than they did.
Yeah, we had a few failures, but we also got to learn what the feeling of seeing a project from start to finish and having it be successful was also like. So that was something that we got from the success, not just the failure.
And the last comment is, your lessons learned were spot on. I've seen those lessons learned over and over again in many different presentations, so you guys did a really good job.
Thank you so much.
Well, I'll echo the comments that have been made so far. I mean, you and your team are awesome. Your presentation was awesome. Your device looks awesome. And I just had a couple of comments. You have an impressive array of highly detailed requirements, which is what you expect to see at a design review. What I don't see very much of is the rationale for some of the requirements. They're just stated, and the assumption is there's some reason why that requirement is there. An example I have in front of me is the hover within a 5-foot circular radius. You know, why exactly you would make a requirement like that, and why it was an electrical requirement. I'm assuming that had something to do with ensuring that the differential thrust from each of the motors was, you know, didn't give you too much error in your ability to deliver. So that must have been where that came from. But I mean, could that have just as easily been a propulsion requirement as well?
Yeah, I think so. We had it in the electrical because at the time it pertained to the flight computer. As for your comment about the rationale as to why, due to time constraints for this briefing, we decided to put those in backup slides just in case it was asked, but it wasn't something that we wanted to take time to explicitly share with everyone. If you'd like to see the rationale behind our requirements, we definitely do have that. We'd love to talk to you about it. But to answer the question about the 5-foot radius, I'd like to hand that to Dakota Brooklyn, who's our electrical lead.
Yes, so the 5-foot radius was actually deemed from the objective, which was land the payload in the desired area. Since our area was a 10-foot area, we didn't want the Hummingbird to move outside that 10 feet, nor do we want the Hummingbird to move too far away and the payload swing outside the area, unable to land inside the objective. So having it move less than half the distance from our desired area, we could then say I felt confident that the system would not swing over the other 5 feet. That was the rationale behind that.
Let me just make one other aesthetic comment. That's that all of you are dressed in almost like uniforms. Was that a requirement for this?
That was my personal requirement. If you're going to be presenting on my team, you're going to look the same.
I'll just comment that I haven't seen engineers dressed like this since I first entered the profession.
Is that good or bad?
The uniform that everybody wore was, especially the white shirt and black tie.
They look like they were driving in.
They all started around like a bunch of penguins. And when I first went to Yale, that was one of the things that I really liked about the place was that people just were sloppy. Thanks.
Thank you.
Once again, just wanted to echo the other panelists' view that you guys did a good job. I enjoyed your video montage. I teared up a little bit because you're all graduating. The only real question I had was for your propellers. You mentioned tests 1, 2, and 4. What the heck happened to test 3?
I'm looking around.
Slide 121, please. Test 3 is behind me, and as you can see, the data
is not very nice. The goal of our thrust test 3 was to compare all the motors to each other to verify that we were getting similar results. Unfortunately, we did this on a very hot day, and the theory is that the thrust stand we used was binding due to thermal expansion inside of its mechanism. Also, the thrust stand that we were using was very difficult to use, specifically in calibration and ensuring a precise starting position, just because of how it was built. But would you please go to the next slide, please, Jennifer? This graph shows the rotational velocity of the propeller for each motor and an average. And as you can see, this data is very close to each other. It's very repeatable. So we were very confident we were getting the same results, even though our thrust values weren't necessarily echoed. Next slide, please, Jennifer. This is also echoed by the current drawn by each motor, which, as I say, is very similar. So we were very confident we were getting the same performance out of each motor. We were just not confident as to what its thrust values actually were.
Thank you. That was all I had.
Well, thank you everyone so much for coming. It has truly been a wonderful process and a wonderful journey throughout these capstone projects. So thank you so much for coming. Have a great holiday season.